Our next talk is VVC for immersive video streaming.
So I'm Sachin Deshpande from Sharp, and I'm going to talk about VVC for immersive video streaming. And this paper is co-authored with Miska Hanuksela from Nokia. So this is the outline. There are basically three things I'm going to describe. One is I will describe some of the VVC features which are especially suitable for immersive video. Then I will talk about how VVC is stored in ISO BMFF. And then finally, how it's streamed for 360 video when you use OMAF, which is another MPEG standard. So as all of us know, immersive video includes 360 video, which is 3 DOF type of video, as well as volumetric video, which may be 6 DOF or where user can move within the video. The VVC standard, when we started the development of it, there were several use cases that were the focus, and some of those use cases included 360 video. So the standard was built, especially a lot of high-level syntax aspects, considering its possible use for immersive video. And OMAF, if you are not familiar, is omnidirectional media format, which is a MPEG standard. And it includes 360 video metadata for ISO BMFF and streaming of that with Dash and MMT standards. And this paper basically provides an overview of these three things: the VVC tools for immersive video, ISO BMFF storage of VVC, and then the OMAF streaming of VVC. So first, let's look at VVC features which are suitable for immersive video. And I picked 4 main topics, and let's go through them one by one. The first one is wraparound motion compensation. It only works in horizontal direction, and the main use case was equirectangular projection, which is shown here for a current frame or a current picture that we are trying to compress and a reference picture. And the idea is that without this wraparound motion compensation, when you have a motion vector which in your reference frame points to a block, part of which is out of the picture boundary, we would previously just do repetition padding, where you just replicate that edge to make the block whole. But for equirectangular projection, it actually makes sense to use the pixels from the left side of the boundary to pad to the right and vice versa. And then that in fact, it was shown that it gives a compression efficiency benefit of about 0.22% BDBR, which is Beyond-Tegard delta bitrate PSNR improvement. It also improves the subjective quality. The next tool is called virtual boundaries, and what happens is, shown here at the bottom is a cube map projection of a 360 video. And the cube map has 6 faces, and that results in some discontinuities, one right across the picture in the middle, and then 2 on the vertical side. And that basically results in VVC has in-loop filters, and you can use tools like subpictures and slices, which are in VVC, and we'll talk a lot more about subpictures in next couple of slides. But you still could have these leaking artifacts because sometimes you might need spatial granularity, which is finer than the granularity supported by subpictures, and then use of subpicture itself results in losing some compression efficiency. So the virtual boundaries is a concept where, for example, for this cube map image that we are compressing, you can indicate a virtual boundary right across the picture, and then you won't do the filtering across that virtual boundary. And similarly, vertically, you can specify boundaries. The standard supports up to 3 vertical and 3 horizontal boundaries, and part of it is used for handling this cube map kind of 360 video artifact removals, but then people also use it for something called gradual decoding refresh, and in that case you can signal these virtual boundaries to change on a per picture basis, whereas for something like cube map you just signal it once in a sequence parameter set because it will be static. Shown here are two types of artifacts, one called leaking artifacts, another called seam artifacts. And the idea is that the leaking artifact is for the areas which are connected but which have irrelevant content. So for example, this boundary right in the horizontal area. And those can be removed by virtual boundary. But the seam artifacts just relate to being able to have different coding tools or coding parameters being used, and those are not removed. This slide was borrowed from a more detailed paper that is in ICASP, which is focused on how to remove both these types of artifacts. So if you're interested, you can look it up or talk to me afterwards. Sub-pictures are something new in VVC, and a sort of predecessor of this, which was built on top of HEVC. It's called Motion Constraint Tile Sets, MCTS. And the MCTS basically is a set of encoder constraints where you have tiles of HEVC and make them into sets of tiles. But sub-pictures improve on MCTS on a number of aspects. One is the boundaries of independent sub-pictures are treated like picture boundaries, so you don't have these aspects of, you can extract sub-pictures independent of each other in that case, and I'll describe several use cases for that. A lot of people think that MCTS constraints are a bit complex for encoder to follow, and sub-pictures don't need those. Then merging of sub-pictures from multiple bit streams is easy and supported. And then you can also even have a combined or merged picture created from different sub-pictures where part of the sub-pictures are IRAP and parts are non-IRAP, and we'll talk about an example which uses that. This shows a comparison of MCTS and sub-pictures. I described many of these things. Some of the other aspects is when you use MCTSS, you need to rewrite parameter sets when you do some kind of bitstream manipulation. And also even slice headers need to be rewritten, which is a bit cumbersome, whereas with VVC, you don't need to rewrite slice headers. Only the parameter sets need to be rewritten. It was actually shown that sub-pictures can provide a compression benefit compared to MCTSS, and up to from 4 to 6% benefit. Some use cases, really quickly, you can have stereoscopic content, each coded as a sub-picture. You can have cube map faces that we saw, each coded as a sub-picture. Viewport dependent streaming, that's one of the use cases I will talk in more detail in the context of OMAF. Texture and geometry of MIV, which is MPEG immersive video, one other MPEG standard for immersive video. You can code each of them separately as sub-pictures. And then some other things such as picture-in-picture, mosaic video, and so forth. For multi-layer coding, I'll try to skip this slide, just mention a couple of things. As opposed to some of the previous standards such as HEVC, where there were the base spec only supported a single layer video, and then the scalability was built on top of it in a subsequent version. VVC base line specification, the version 1 spec itself supports multi-layer coding. There is this interesting concept that you of course can use inter-layer prediction from base layer to enhancement layer, but you can designate that I'm only going to use IRAP pictures for inter-layer prediction, or I'm only going to use temporal ID 0 and 1 pictures for prediction of enhancement layers. There are a few use cases for using multi-layer coding for immersive video, and one of that is again stereoscopic video, where each of the views of stereo could be coded as layers, and then you can have dependent view coded from the independent view to get compression efficiency. If we have independent view of 360 at a basic resolution and quality, and then we can have dependent layers which enhance just part of the viewport. That's one other use case. And then again, this texture and depth aspect, which relates to MIV, where you can have a single bit stream, each coded, texture and depth are coded as different layers, and you can use interlayer prediction. Next topic, so the second topic is storage of VVC in ISO BMFF. As you can expect, since we have this concept of sub-pictures, you can do some fancy things in ISO BMFF to designate those such that they can be used. And I tried to summarize some key and some exotic or niche aspects that are supported in ISO BMFF in terms of VVC tracks. The first type, there are 5 different types of VVC tracks that I want to quickly describe. The first is a VVC sub-picture track, which basically is a sequence of sub-pictures. The next is a very special case called substitute sub-picture track. So you can have these arrangements of different resolutions being used for immersive streaming, and you might result in a case that you have sort of a hole in your, the entire thing still has to be a rectangular overall picture. And if you have like a area which is not used, you can designate it as a substitute sub-picture, which is basically like a dummy empty sub-picture. The VVC merge base track allows you to take several different VVC sub-picture tracks and put them together. So it's like a recipe of how to create your overall picture. VVC extraction based track is a slightly simpler case. It deals with a single VVC track and how to just extract some of the sub-pictures from it, so like a ROI kind of use case. And then finally, VVC non-VCL, which is non-video coding layer track, relates to parameter sets and other NAL units that do not contain coded video data. So now the final piece, the OMAF, which deals with the streaming of 360 VVC video, and there are 2 main profiles in OMAF 3rd edition, which is where the support for VVC was added. And the first one is VVC-based viewport independent profile, and the second is VVC-based simple tiling profile. Both of them support VVC main 10 and less than or equal to 10 bits as the bit depth. The viewport independent only supports equirectangular, and both equirectangular and cube map is supported by the tiling. Then let's look quickly at the 2 of those. I'll very quickly talk about viewport independent. It's basically like a simple profile where you encode the entire 360 video, typically all at the same quality, and then you can create several different bitrate versions of it, just like how it's done in Dash for 2D video streaming. And then the client chooses one of it and you just decode it. So it's a simpler setup. The more interesting is the viewport dependent streaming, and roughly there are 2 main ways of doing viewport dependent streaming. One is called viewport specific, and the other is called tile based, where the word tile has some legacy in the OMAF spec, and in general in people said. So in the context of VVC, tile refers to sub-pictures, actually. So what is the difference between 2? The viewport specific relates to VVC bit streams that are encoded and encapsulated in its own VVC track, and then you can create several different ones of those where each may be targeted to a certain viewport. So depending on your content, you can typically know where the users look and create streams that are catered towards it. And there is something called RWQR, region-wise quality ranking metadata that OMAF describes, which then it can be included in the Dash MPD, and then the client can see that and decide, okay, what's my viewport, so which stream should I request? And then it just gets one VVC track. As opposed to that, the sub-picture based is interesting, where you can get sent multiple VVC sub-picture tracks and this VVC merge based track. So this is my last example slide. I think the illustration is a little bit small here, but quickly what I want to show here is what OMAF allows you to do is a use case such as this, where the top 2 are one IRAP period and 2 different qualities, and this one is the one where the black one and the red one is the one which has longer IRAP period, which means you can have a better compression efficiency. And the bottom one, again, there are 2 qualities, and it has shorter IRAP period, so that can be used when you suddenly move your head. We can send you the data from this representation to give the viewport at a highest quality. And so then here is the ISO BMFF track representation of it. There are each number here is a sub-picture ID, and each of them is a sub-picture track. This is the merge base track, and then what gets sent to the client is, so let's say initially you are receiving 1, 2, 5, 6, and 13, 14, 17, 18, and then you continue to get that, and when you move your head quickly, you get sent something from this shorter IRAP duration track such that your viewport, and so in this case, the client gets this picture which is composed of these various sub-pictures, and it can have this property that in your viewport you have IRAP sub-pictures only, and in the non-viewport part you have non-IRAP sub-pictures, and that is something very unique to VVC. So again, this is described in detail in the paper, and I encourage you to look at it. Finally, conclusion, basically I want to describe the VVC standard, the ISO BMFF storage of it, and how OMAF streams the video. Thank you for your attention, and any questions?
All right.